All right, hello. So last week of recorded lectures. Okay, so we're going to continue today talking about uh, velocities for rigid bodies. And so remember sort of the story that we had last time was that we had a rigid body in motion. So remember that what that means is we have a spatial frame and a body frame. Oops. And then we have a vector, little r, which goes from the spatial origin to the body origin. And then there's a big R. And in motion simply means that we have a curve in SO3 cross R3. Okay. And we defined the body angular velocity, and it was defined by working with the rotational component. And remember that we had this, I will frequently, I'm afraid, forget to put hats and things on vectors. So sometimes I'll write omega when I really meant omega hat. So here I mean omega hat. So I can either make that omega hat or I can put a big check over that, either way. But this is the body angular velocity. And then the spatial angular velocity is kind of the other way around. And then, so, last time I sort of mentioned that this was going to be just a convenience that we're going to do that's incorrect. And that's we're going to write this R dot, which seems like it should be the natural physical quantity, but somehow it's not. But nevertheless, we're going to call this both body and spatial translational velocity. Okay. All right, so so we spent a bit of time at the end of the lecture last time talking about what these things mean, especially the angular velocities, about axes of rotation and stuff like that. Today, we're going to just sort of continue to think about how to interpret these things, and start working this out for a couple simple examples. Okay. So the way I've talked about these velocities so far is I've thought about taking a rigid body and having it be in motion. Well, you can do the same kind of a thing for not just for a single rigid body, but for an interconnected mechanical system. So if we have an interconnected mechanical system with, and so up until this point, I've kind of allowed an interconnected mechanical system to be comprised of particles and bodies. And having to do both of those things is just tedious after a while. So I'm going to now just stop including particles and just talk about bodies. And we'll see later on in the course that this, in fact, can be done without loss of generality. So, in fact, particles are rigid bodies in a certain sense. Okay, but for now, we're just going to discard particles. Okay, so we have an interconnected mechanical system with m rigid bodies. Okay, and configuration manifold. Q, which, remember, our definition of an interconnected mechanical system was that the configuration manifold was a submanifold of Q free. And in this case, Q free, because we have m rigid bodies, is just m copies of SO3 cross R3. Okay. So you can now easily talk about the kind of total velocity of this system, and it's simple to do, and it's really once you've sort of gotten the single body ideas down, the rest of it's kind of just notation. And so, but let's go through and do that. Okay, so let's denote by pi a, and so this is a map from Q into SO3 cross R3, the projection onto the 8th component of this product. Okay. And so I'll write down exactly what that is. Okay, so pi a takes a point in Q, but what's a point in Q? Well, a point in Q, after all, is just a point in Q free. All right, and so every point in Q I can write as R1. Oops, sorry. R1 up to RM. Right? And this just encodes, and there's going to be restrictions on how our big R's and little r's are related to each other, coming from the interconnections, as we've seen in the examples. But nevertheless, you can write a point in Q like this. Okay. So this is simply RA. Okay, and so this is what's called the 8th forward kinematic map. Okay, and it's very simple. Mathematically, it's simple, and physically, it's simple. Mathematically, it's just what I just wrote. It's a projection, right? Just taking m of these and returning the 8th one. And physically, it's also very simple. It just takes all of the bodies that are in some configuration, and the configuration is labeled by that, and it returns the configuration of the 8th body. Okay, so physically and mathematically, this is a very simple thing. But it's also a very important thing, and we're going to make great use of this thing. And so let's, for example, see how we can do that now. So we wish to represent the velocity of the system. Okay, so the system means the interconnection of these m bodies, and they're all going to be in motion somehow, and they're all going to be in motion in such a way that they satisfy the constraints prescribed by Q, and we want to represent the velocity of that. Okay, as it undergoes a motion. And now a motion is going to be a curve, and I'm going to call the curve gamma. And so gamma is going to be in Q. Okay, but gamma's in Q, which is also in Q free, and so we simply write, of course, this motion okay, and so we basically have m versions here of the thing that we considered here for a single body. Okay, so that's nothing exotic. All right. So what we want to do is, so the velocity of the system at time t. Okay, so there's multiple ways that you can think about this. Okay, if you were just kind of forgetting about the fact that it had all this complicated SO3 cross SO3 cross, sorry, SO3 cross R3 cross SO3 cross R3 m times behavior, and you just wanted to think about gamma as being a curve in this manifold Q, the configuration manifold in this case, then the velocity could just be gamma prime. Right, and this gamma prime is the same thing that we talked about when we talked about gamma prime for arbitrary curves on manifolds. Remember, there was a very specific definition for this. So the definition was that this was t at t gamma, okay, applied to the tangent vector 1. Okay, so this looks really like weird notation. So let me just remind you where this comes from. So gamma is a curve in the manifold Q. T gamma is then a map from between the tangent bundles, as we've talked about. Okay, T gamma is the restriction of T gamma to the tangent space at little t of the interval I, okay? And this is R, okay? Because I is an open subset of R, tangent spaces of open subsets of Euclidean space are naturally isomorphic to the Euclidean space. In this case, the Euclidean space is the one-dimensional Euclidean space, okay? All right, and so therefore gamma prime is just what I wrote. Okay, and so it's applied to, right? So it's applied to an element of this tangent space. An element of the tangent space is just a number, and that number we choose is 1. Okay, so that's how we defined gamma prime. All right, so we did this before, I'm just reminding you. Okay, all right, so now, now we have that RA of t, little ra of t, okay, well, this is equal to pi a at gamma of t, right? So gamma is a curve in Q, like so. Q sits inside Q free, like so. And RA and little ra are just the projection onto the mth component of this thing, right? So that's just true, okay? And so therefore, I can differentiate this. Okay, and I get, okay, so now I'm going to differentiate this expression with respect to time. Excuse me. And so this is the derivative of a composition, right? The composition of pi a with gamma. And so, you know, when you differentiate compositions from calculus, those you differentiate using the chain rule. And so there's a chain rule for t, you know, the derivative t that we talked about before. And so I'm going d by dt of pi a composed with gamma of t, and by the chain rule, and the chain rule in this case looks like this. It looks like t gamma of t pi a composed with t gamma, tt gamma, and because I'm taking the normal time derivative, I put this 1 here, okay, evaluated at 1. Okay, so in other words, this is t gamma of t pi a at gamma prime of t. Okay. So why did I do this? I did this because what we're going to, this is, one version of the way of thinking about what the velocity of the system is, right? It's kind of the forget about all the physical structure and just focus on the mathematical structure of Q being a manifold, then the velocity is just that. Okay, now we're going to try to get the physics back again. And so what we want to do is we want to relate this to stuff we already know about. Okay, and this is how you do it. You do it through the derivative of this forward kinematic map. Okay. All right, so this then gives two representations of gamma prime. Okay, and when I say two, I mean two come one body and one spatial. Okay. All right. Okay, so now another way to think about this. So since gamma prime is just some tangent vector, one can think of these representations as mappings from TQ, right? That's where gamma prime lives, or gamma prime here, into these rigid body velocities that we talked about before. Okay, and so these are going to map into, all right, so it's going to be, well, first, so this is a tangent bundle, and so I'm going to need, Q, okay, but Q, inside Q free, which is all of this, okay, and so this really is in SO3 cross R3 to the M, okay, that'll be kind of the Q part of the representation. Then I need the velocity part, and the velocity part, again, is going to have these two representations, body and spatial, but they both kind of have the same, they look the same. They look like R3 is going to be the angular velocity, and then there's going to be R3, which is the translational velocity. So the idea is that this part here is configuration. Okay, inside Q free. Okay, and then here we have angular velocity, and it'll be either body or spatial. And then translational velocity. Okay. And so explicitly. So now I'm going to just go and write all these things down. Okay. So I'm going to have TQ is a subset, is a subset of T of Q free. Okay, because Q is a subset of Q. And so this, again, is a subset. So Q free, remember, is SO3 cross R3. SO3 sits inside R3 by 3 cross R3 M times. Okay, and so therefore, we're going to write an element of TQ, sorry, as, okay, so it's going to be a big long string of stuff, but all of it's very simple. So first there's going to be the Q part, and the Q part looks like that. Okay, so it's going to be R1, R1, RM, RM, okay. Okay, so this is the part inside Q free. Okay, and then you have the velocity part. Okay, and the velocity part I'm going to write like this: A1 V1 AM VM. Okay, now this is in R3 by 3 cross R3. Okay, and similarly for this one, of course. And the way you should think about A is being R dot. Okay, it's the velocity of a point in TQ, which is a point in TQ free, which is a point in the tangent bundle of M copies of R3 by 3 cross R3, which is equal to that, right? So it's a big, complicated mess, each separate component of which is very simple, but then when you get to the end to write everything down, it's just a big long expression. So I have big R, little r, and I have M copies of those. Okay, and then I have I have A's and V's, and the way you should think of these is as being velocities. A is being the big R component of the velocity, i.e. R dot, and V as being the little r component of the velocity, which is little r dot. Okay. All right. So then we have these two mappings, and I'm only going to write one of them out explicitly. The other one is defined in the same way, except one's body and one's spatial. Okay, so I'm going to define iota body. This is going to be a map from TQ into Q TQ free. Okay, and what is this map explicitly? Okay, well, we've already decided that a point in TQ we can write like this. All right, so that's what I'm going to do. So let me write it all down again. So R1, R1, RM, RM, A1, V1, AM, VM. Okay, and this maps to, okay, so it's going to map to a point in TQ free. Okay, but points in TQ free, you know, they assume the same form, except now I'm going to write them. Sorry, I apologize. I don't mean to. I didn't mean to write that here. What I meant to write here was, sorry, SO3 cross R3 M times cross R3 plus R3 M times, okay? And so the point is that I'm using this is the Q free part, and this is going to be the velocity part, okay? So here I go. The Q part is the same, right? So I'm mapping here into here, and it's, you know, just the identity on that part. Okay, and then what am I going to get in the in this component? Well, I'm going to get the because I'm using body here, I'm going to put the body angular momentum here, and then the body angular velocity here, and the body translational velocity here. Okay, so that's capital omega and little v. Okay, and what does capital omega look like? Okay, well, capital omega looks like R transpose, and the definition, so R1 transpose, and the definition would be that I would put R1 dot there, right? But R1, the role of R1 dot here is being played by A, okay, like so. So it's A1, okay, and then I have the body translational velocity for the first body, which is V1, and so on. Okay, and then similarly, I have we have iota spatial. Okay, and of course, the only difference is that in these components, I'm going to put R transpose, because it's the spatial angular velocity. Okay, so this is a lot of stuff, but this is really void of any conceptual content. It's merely notation. And it just gives me a way of organizing all of my information about the kinematics of my system, right? The position and the velocity, it gives me a way of organizing that into one big thing, okay? And that's all it is. It's just sort of a way of writing everything down together that represents all of the kinematic information about the system. So what does that look like in practice? Okay, so let's look at some examples. Okay, and as you'll see, this is just very, very simple. All right, so let's look at the examples that we've looked at. Okay, so it's the planar rigid body. Okay, and we decided that Q free, and so really you remember to write down Q, a point Q in Q free. Because we only have one body, Q free is just SO 3 cross R3. And we decided that Q was the set of R's in Q free. Okay, and then we had a form that we had for big R and little r. And the form was very simple. So R was cos theta minus sine and sort of, yeah, it's plus sine. So sine theta minus sine theta cos theta. Okay, so R looked like that, and little r looked like that. Okay, and you know, x, y, theta were arbitrary reals here. Okay, good. So that's what Q looks like. Now what we're going to do is we're going to write down what this thing is. And what that amounts to is that really just amounts to doing the very elementary stuff that we did last time, which is calculating the body and the spatial angular velocities. Okay, so you do that just by, you know, elementary differentiation. Okay. All right, so you just do simple time derivatives, nothing complicated. Okay, so I'm doing time derivatives, and so, you know, I need to use the, you know, infamous chain rule to do time derivatives, and so there's a theta dot that comes out in front of all that. Okay. Okay, so now you, to calculate the, say, body angular velocity, well, the definition is simply R transpose, R dot, check. Okay, and if you do the matrix multiplication, what you get should be 0, theta dot, 0, 0, 0, 0, 0, 1. Oh, sorry, 0. Okay, and again, it's checked. Okay, and so if you look at the rule for the hat map, which takes an element of little SO3, which is a skew symmetric 3x3 matrix, and returns for you a 3 vector. Okay, you'll remember, you'll see how that looked, is that it had, you know, the third component was here, the second component was here, and the first component was here. So in other words, this, when you translate it into a 3 vector, is 0, 0, theta dot. Okay. Now this is physically exactly what we talked about last time. So first of all, this angular velocity is only in the S3 direction, and this corresponds to the fact that I'm, as my body moves around on the plane, the rotations are rotations about the S3 axis. Okay, so that's why the body looks like that. Well, that interpretation actually would be for the spatial velocity, but it turns out the spatial velocity is exactly the same. Because remember that the spatial velocity is as a vector in R3 is the axis about which the body is instantaneously rotating at time t. And then, so that's the spatial velocity, and then the body velocity is the same thing, but viewed from the body frame. And because the body frame has the same sort of B3 vector as the spatial frame's S3 vector, that's why these two things are actually the same in this case. Okay. All right. And then V is equal to, of course, x dot, y dot, 0. Okay. All right, so now let's do the thing that I did up here. Okay, let me write down all of this stuff. Okay. Okay, so what we saw when we talked about just the configurations for this system, we saw that x, y, and theta were coordinates for Q. Okay, and so when I'm going to write down now this mapping, okay, I'm going to write this mapping down in coordinates. Okay, so I'm going to use the coordinates that I've chosen to use for Q, which are x, y, and theta, and then the corresponding coordinates for the tangent bundle, which I'm going to call Vx, Vy, and V theta. I'm going to use those as coordinates for TQ. So what I'm really writing down here is the local representative of iota. Iota spatial and iota body will be the same in this case, just because of the coincidence that these things are the same. Okay, so a point in TQ I'm going to represent in coordinates as x, y, theta, x dot, y dot, theta dot. Okay. So we have the local representative of iota body is, okay, so it's going to take a point in TQ, right? Because that's what iota body does, and it's going to give me all this stuff. Okay. Okay, so it's going to take x, y, theta. Oh, sorry, I didn't mean to do this. I don't want to think of these as being functions of time now. I want to think of them as being coordinates in the tangent bundle, in which case this is Vx, Vy, and V theta. Okay. All right. And so it's going to give me all of this stuff. Well, thankfully, there's only one, m is equal to 1, so it's not so bad. Okay, but still. Okay, so the first bit is going to be cos theta minus sine theta. And I'm waffling here on where the minus sign goes. Let's see. So it's going to be, yeah, the minus sign goes here. Cos theta 0, 0, 1, 0, 0. Okay, so that's big R. And then little r is x, y, 0. Okay. And then I have, I'm sorry, I did this again up here. I apologize. I meant to check these. These should be vectors in R3. Okay. We're doing the unhatted versions of those. Okay, so I'm going to write down now the two vectors in R3, the body angular velocity as a vector in R3, which looks like this. V theta, Vx, sorry, as a vector in R3, it looks like 0, 0, v theta, that's the angular velocity. And then the translational velocity is vx, vy, 0. Okay. All right, so that's what this mapping looks like in this case. And you can see that, again, all this is doing is it's just encoding the simple calculations that we've already done, right? It, Q looks like that, right? With Q looking like this, R dot looks like this, and omega are given by these formulas. And so it's just assembling everything into a single thing, right? So it's big R, little r, in this case it's body, so it's little omega, and then v, all right? And so similarly, of course, you have the spatial version. Okay, so just writing all this stuff down takes a moment, but really, again, it really suffices to just write down this, 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 and this, and then and then this. Okay. All right, let's look at another example. Okay, let's look at our stupid robot example. Okay, and here we had Q free equals SO3 cross R3, like so. Okay, and so, here I took the time in this simple example, because I had only one body, I took the time to assemble all of these things into their, big, long, concatenated list, right? I'm not going to do that anymore. I'm just going to write down, because I have two bodies here, so there's 2 3x3 matrices, and to write the whole thing down, takes too much screen space. So I'm just going to write down big R1, big R2, little R1, little R2, and then big omega and little omega, and then the translational velocity v, okay? So the big R's and little r's, we've already written those down in our previous visitations to this example. Okay, and so we had this angle theta 1, and we had this angle theta 2. And so let me save myself some effort here and just okay, so the capital R's look like this. I had a little r. Okay, and little r was 1/2 L1 cos theta 1, and then 1/2 L1 sine theta 1, 0. And then little r2 was L1 cos theta 1 plus L 1/2 L2 cos theta 2, and then L2, sorry, L1 sine theta 1 plus 1/2 L2 sine theta 2, 0. Okay, so that was R2. Okay. All right, and then we have the angular velocities and the translational velocities. Okay, and so you'll notice that the form of R here is exactly the same as we had here, and so therefore the form of the omegas will also be the same. Okay, and so omega A is 0, 0, theta A dot, okay? And we can write that as 0, 0, V theta theta A. And let me maybe just write it as VA, save the theta, since we don't really need it. Okay, and then omega A also is 0, 0, theta dot A, 0, 0, VA. Okay, and so again, this is just representing it as a derivative along a curve, and this is representing it as a coordinate for a point in the tangent bundle. The way to do calculations is easier to use the derivatives, but then after you have the derivative, you can replace it with the tangent bundle coordinate. All right, and then you have R1. Okay, so now you have to go and calculate the stupid thing, and so it's going to be 1/2 minus 1/2 L1 sine theta 1, and then you're differentiating with respect to time. So this is sorry, not R1, it's V1. Okay, so you're differentiating with respect to time, so it's going to be theta 1 dot, and let me write that instead as V1. Okay, and then here I'm going to have 1/2 L1 cos theta 1 V1 0. Okay, and then V2 is going to be L1 sine theta 1 V1, sorry, minus, and then minus 1/2 L2 sine theta 2 V2, and L1 cos theta 1 V1 minus, sorry, plus 1/2 L2 cos theta 2 V2 0. Okay, and so if you wanted to, you can take and assemble all of this stuff. Okay, so there'll be 8 of these terms, right? It'll be R1, big R1, little R1. Big R2, little R2, then omega 1, and then V1, and then omega 2, and then V2. And you can do just like I did up here, and you could assemble those into this big long expression to get iota body and iota spatial, right? But the point is that all those are really doing is they're just organizing that information. Okay. So the point is, you can organize this into iota body and iota spatial. Okay, and then our third example was this rolling disk. Okay. Okay, so let me not label all the stuff that we have already labeled in the past. Okay, and so here we just have a single body, and so here Q free is just SO3 cross R3, and so the representations are simple in that sense. It's just a single body, but remember that we had a rather complicated procedure for figuring out what capital R was in this case, right? So it's not obvious how to figure out capital R. So, but we kind of just slowly did this in a systematic way. And then we had little r was x, y, and then rho, where rho was the radius of the disk. Okay. And then you can now just calculate, right? You can calculate okay, so I never actually explicitly wrote down what this thing was, but if I did, I could certainly calculate R dot and R transpose, and I could do matrix multiplication, and I could convert the resulting vector from the resulting 3x3 skew symmetric matrix into a 3 vector, okay? And you get something. It's not that complicated, but I certainly don't remember what it is. And the point is that you get some expression that I kind of, if you write it down and you screw your eyeballs a little bit, you can make yourself believe that you could have guessed that, okay? But if you tell me that, I kind of won't believe you. Okay, and similarly for the translational, the spatial angular velocity is equal to something. And the best place to actually store this information when you're doing these calculations is in your computer. Use some sort of a symbolic manipulation package. So I got an email the other day saying Queens is now subscribed to Mathematica. Mathematica is the package I prefer to do symbolic computations. Maple is another one, whatever. But the best place to do calculations with these examples is in a symbolic package like that. Then you don't have to make mistakes transcribing things. Okay, and then V is, of course, Vx, Vy, 0. Okay, and again, just like in the previous examples, you can assemble all this information into a big long thing if you wanted to. Okay. All right, so that kind of brings to a close, a part of the course where we kind of have talked about how to model representing positions and velocities of systems, okay? And we've seen how to do that in a geometric way, and we've seen how to take those geometric tools and convert it into physical things. What we will do next time is, we're going to talk about kinetic energy. Okay, because it turns out that kinetic energy is an important ingredient in writing down equations of motion for these kinds of systems. Okay, so that's next time.